Section: Introduction. In this section, we introduce the concept of Standard Prompt-Based Large Language Model (LLM) inference, which consists of two main stages, prefilling and decoding, as illustrated in the generation pipeline figure. During the prefilling stage, we compute and store the key value (KV) cache for each token in the prompt and predict the first token. We refer to the time taken in this stage as the time to first token (TTFT). After prefilling, we enter the decoding stage, where we use the cached KVs to iteratively decode the next token until we meet our stopping criteria. In the prefilling stage, all tokens from the prompt are processed by every transformer layer. For longer prompts, TTFT can be slow because modern transformer-based LLMs are both deep and wide, leading to a quadratic increase in the attention computation cost as the number of tokens grows. For example, Llama 2, which has 7 billion parameters, consists of 32 transformer layers with a model dimension of 4096. In this case, TTFT can take 21 times longer than each subsequent decoding step and accounts for about 23% of the total generation time on the long bench benchmark. Therefore, optimizing TTFT is essential for making LLM inference more efficient. While there is ongoing research aimed at improving LLM inference, many methods have concentrated on speeding up the decoding stage, with less focus on enhancing TTFT. We observe that some compression-based approaches indirectly improve TTFT by reducing the size of LLMs. However, another line of research looks specifically at how to enhance TTFT while keeping the transformer architecture unchanged. A key question in this area is whether all prompt tokens are necessary for generating the first token. Our profiling of LLMs on the long bench benchmark shows that the attention scores of input tokens relative to the first generated token are quite sparse, suggesting that many tokens in the input prompt are unnecessary and can be removed without impacting the prediction of the next token. To address this, we propose LazyLLM, a new and straightforward technique designed to speed up the prefilling process. As shown in the teaser figure, LazyLLM selectively computes the KV for only the tokens that are important for predicting the next token and, lazily, postpones the computation of the remaining tokens until they are needed later. We suggest using the attention score from the previous transformer layer to assess the importance of tokens and progressively eliminate less important ones as we move deeper into the transformer. Unlike prompt compression methods that permanently reduce the prompt for all future generation steps, our approach allows the model to reintroduce previously pruned tokens, which we found to be vital for maintaining accuracy. Extending this progressive token pruning to all generation steps is complex. Specifically, if we prune a token at one generation step and then revive it at a later step, we need to recompute some hidden states during that later step. To avoid this repetitive computation, we implement an additional caching mechanism called OxCache, which stores the hidden states of pruned tokens. This allows us to efficiently revive pruned tokens and ensures that the worst-case runtime of LazyLLM is never slower than the baseline. In summary, the benefits of LazyLLM include: 1. It can be easily integrated with any existing transformer-based LLM to enhance inference speed. 2. It does not require any fine-tuning and can be implemented directly without modifying parameters. And 3. Empirical results across 16 standard datasets and 6 different language tasks demonstrate that LazyLLM improves the inference speed of the LLM during both the prefilling and decoding stages. Next, we discuss related work. The growth in the size of large language models has significantly improved their performance but has also created challenges regarding inference efficiency. The inference process for generative LLMs consists of two distinct stages, as shown in the generation pipeline figure. Notably, extensive computation is required in long context scenarios to calculate the full KV cache during the prefilling stage, leading to a lengthy TTFT. This delay can result in users waiting several seconds after submitting a prompt before receiving a response, which negatively impacts user experience. To enhance inference efficiency for long context applications, various methods have been proposed to reduce memory usage and total computations. Some approaches have focused on modifying the transformer architecture for long context inputs. For instance, one method introduces a drop-in replacement for standard self-attention, combining local windowed attention with task-specific global attention. Another approach, reformer, replaces traditional dot product attention with a method that uses locality-sensitive hashing to lower computational complexity. While these methods can accelerate long context inference, they require significant changes to the model architecture and retraining, making them impractical for existing pre-trained LLMs. Closer to our work are techniques that optimize the KV cache by minimizing its size and data transfer. However, these methods primarily focus on speeding up decoding steps and do not address the reduction of TTFT. Previous research on tasks like sentence classification has shown that not all tokens in an input sequence are necessary for making accurate predictions. This opens up opportunities for token pruning, which reduces computational demands by selectively removing less important tokens during inference. For example, one study presents learned token pruning, which adaptively eliminates unimportant tokens as they pass through transformer layers. Another approach aims to reduce width-wise computation through token pruning in transformer-based models like BERT. These earlier methods were designed for tasks that require only a single processing iteration, such as text classification. In our work, we extend the concept of token pruning to generative LLMs. Specifically, our method allows the model to dynamically select different sets of tokens at each generation step, which is crucial for maintaining performance. Additionally, we introduce Oxcache to ensure that each token is computed only once throughout the entire generation process, guaranteeing that the worst runtime of our method does not exceed that of the baseline. Section Summary. In this section, we describe the two stages of standard prompt-based LLM inference, pre-filling and decoding, highlighting the challenge of long time to first token, TTFT, due to extensive computations in the pre-filling stage. We introduce LazyLLM, a technique that selectively computes important tokens and defers others, allowing for efficient inference without requiring model retraining, while also ensuring that previously pruned tokens can be revived when necessary. Section: LazyLLM. In this section, we provide background on the inference process of generative large language models, LLMs, which consists of two main stages, pre-filling and decoding. During the pre-filling stage, we input a prompt made up of a sequence of tokens, and the model calculates and stores the key value, KV, cache for each token while generating the first new token. The architecture we typically use is a transformer, which is made up of several layers. Each layer has a similar structure that includes a multi-head self-attention mechanism followed by a multi-layer perceptron, MLP. The time taken during the pre-filling stage is known as the time to first token. After pre-filling, we move on to the decoding steps, where we add the generated token to the input and then decode the next token. This process continues until we meet our stopping criteria. Although the calculations in each decoding step are similar to those in the pre-filling stage, they require significantly less computation because of the KV cache. Specifically, since we have the KV cache from the pre-filling stage, we do not need to process all previous tokens through the linear layers of the model again. Now, let's discuss our proposed LazyLLM framework. This framework begins with the full context and gradually removes tokens to decrease the number of computations as we progress through the model. Importantly, LazyLLM allows us to choose different subsets of tokens from the context at each generation step, even if some tokens were removed in earlier steps. This dynamic pruning is more effective than static pruning, which removes all tokens at once, as it optimizes the prediction of the next token at each step, helping to maintain performance. Before our work, token pruning had been used to enhance LLM inference, but those methods required gathering full attention maps to assess the importance of prompt tokens before starting the pruning process. This meant they could not effectively reduce the time to first token since they still needed to compute the entire KV cache during the pre-filling stage. In contrast, LazyLLM computes only the important tokens needed to predict the next token right from the first iteration of inference. A significant challenge we face in pruning tokens during the first iteration is figuring out which tokens are important. Drawing inspiration from previous research on early exiting, which shows that token hidden states evolve through the transformer layers, we implement layer-wise token pruning at each generation step. We use the attention map from a specific layer to assess the importance of each input token concerning the next token we want to predict. After calculating the confidence scores for the tokens, we encounter the challenge of setting a threshold for pruning. This threshold can vary because the distribution of attention scores changes across different layers and tasks. To address this, we use a top K percentile selection strategy for pruning. Specifically, we prune a token if its confidence score is below the KTH percentile among the input tokens at that layer. Once a token is pruned, it is excluded from all subsequent computations, meaning that the tokens used in later layers will only be a subset of those from earlier layers. Our experiments show how performance changes based on where we prune tokens and how many we remove. We found that when we prune at the same transformer layer, the model's performance decreases as we keep fewer tokens. Additionally, pruning later in the transformer layers tends to yield better performance than pruning earlier, indicating that the later layers are less affected by token removal. To strike a balance between speed and accuracy, we apply progressive pruning, retaining more tokens in the earlier layers and gradually reducing the number of tokens as we approach the end of the transformer. In the prefilling stage, we do not have a KV cache, and every token is represented by hidden states. Therefore, we can implement progressive token pruning by removing the hidden states of pruned tokens. However, extending this pruning to the decoding steps is more complex because each decoding step relies on the KV cache computed during the prefilling stage. Since LazyLLM performs progressive token pruning during the prefilling, the KV cache for tokens pruned at a certain layer will not be available in the next layer's KV cache. Importantly, LazyLLM allows each generation step to select a different subset of tokens from the full input sequence, regardless of whether they were pruned in previous steps. For instance, during decoding, pruned tokens that are not in the KV cache of the next layer may be reselected for attention computation. However, since we cannot retrieve the KV cache for these tokens, a straightforward solution would be to process them again from the beginning of the transformer, which would lead to redundant computations and slow down the entire generation process. To overcome this issue, we introduce an aux cache alongside the original KV cache. This aux cache stores the hidden states of pruned tokens if their KV is not available in the next layer's KV cache, allowing us to retrieve them for future iterations. In each decoding step, each transformer layer first checks for the KV cache of past tokens. For tokens not found in the KV cache, we can directly access their hidden states from the aux cache of the previous layer, avoiding the need to pass through earlier layers again. This approach ensures that each token is computed only once per transformer layer, maintaining the efficiency of LazyLLM and ensuring that its worst-case runtime does not exceed that of the baseline model. Section Summary. In this section, we describe the LazyLLM framework for optimizing large language model (LLM) inference through progressive token pruning, which dynamically selects important tokens at each generation step to reduce computations while maintaining performance. We also introduce an aux cache to store hidden states of pruned tokens, allowing for efficient retrieval during decoding without redundant computations, ensuring that the overall runtime remains competitive with baseline methods. Section: Implementations Details. In this section, we implement LazyLLM on the Llama 2 and X-Gen models and evaluate its performance using the long bench benchmark through Hugging Face. We adhere to the official guidelines provided in the Long Bench GitHub repository for data preparation and prompting in all our experiments. The Long Bench benchmark includes various datasets across different tasks, each with its own set of evaluation metrics, such as Rouge L, F1, accuracy, and edit similarity. Following the established evaluation process, we organize our results by calculating the average scores across major task categories. As we mentioned earlier, LazyLLM does not require any training, so we utilize the same existing checkpoints as our baseline for all models. For our experiments, we run everything on NVIDIA A100 GPUs and measure the speed improvements based on actual time taken. Specifically, for the TTFT speedup, we look at the time from when we input the prompt into the model until the model produces the first token. For the generation speedup, we measure the time from the prompt input until the model has finished generating all output tokens. To ensure accurate timing, we perform 5 warm-up runs for each experiment to eliminate any noise, such as the time taken to load model parameters. In our experiments, we test our method using 2 large language models, Llama 2 with 7 billion parameters and XGen with 7 billion parameters. We compare our approach against baseline models using the same publicly available pre-trained checkpoints, without any additional training. Our experiments utilize LongBench, which is a multitask benchmark designed for understanding long content. LongBench consists of 16 datasets and encompasses 6 tasks, including single document question answering, multi-document question answering, summarization, few-shot learning, synthetic tasks, and code completion. For evaluation, we focus on the effectiveness and efficiency of each method in terms of the trade-off between TTFT speedup and accuracy. In this context, accuracy refers to the average scores across datasets for each task, while TTFT speedup indicates the time improvement compared to the baseline for generating the first token. Additionally, we analyze the impact of our method on the percentage of prompt tokens computed and the overall generation speedup. The percentage of prompt tokens computed reflects the total amount of prompt tokens processed by the end of the generation, indicating how much computation we save. The generation speedup measures the time change compared to the baseline for completing the entire generation process. Our results, presented in a table, compare the TTFT speedup and accuracy between LazyLLM, standard LLMs, and other baseline methods. In this table, the term baseline refers to the standard LLM inference, while the random token drop baseline involves randomly removing prompt tokens before inputting them into the LLMs. We report average metrics from 5 runs for the random token drop baseline. Our static token pruning baseline removes input tokens all at once based on their attention scores from the initial transformer layers during the pre-filling stage. We also compare our method with a prompt compression technique that reduces redundancy in the input context using LLMs. The results show that LazyLLM consistently achieves better TTFT speedup with minimal accuracy loss across various tasks. It is important to note that the overhead associated with running LLMs for prompt compression is quite high. Although inference on the reduced prompt is faster, the actual TTFT for the prompt compression baseline is longer than the standard baseline. The efficiency of LazyLLM is influenced by 3 key parameters: the number of pruning layers, the locations of these layers, and the number of tokens pruned within them. By increasing the number of pruning layers and removing more tokens, we can optimize computation by processing fewer tokens. Pruning tokens earlier in the layers can also save computation for the subsequent layers. Adjusting these factors can lead to greater overall computation reduction and improved TTFT speedup. However, excessive pruning may result in loss of information and a decline in performance. Similarly, the TTFT speedup and accuracy of baseline methods can vary based on different hyperparameters. We compare TTFT speedup and accuracy with various hyperparameters, and our visualizations indicate that, without any training, LazyLLM maintains better accuracy than the baselines for the same TTFT speedup. For instance, our method can achieve a TTFT speedup of 2.34 times in the multi-document question answering task with a negligible performance loss of less than 1%. By managing the pruning parameters, LazyLLM strikes a good balance between accuracy and inference speed compared to baseline methods. For example, LazyLLM can achieve a TTFT speedup of 3 times in the multi-document question answering task with a maximum accuracy drop of 10%. In contrast, baseline methods experience significant accuracy degradation for similar TTFT speedups. It is also worth noting that prompt compression methods do not improve TTFT due to the overhead involved in the compression process. Section Summary. In this section, we describe our implementation of LazyLLM on Llama 2 and XGen, evaluating it using the long bench benchmark without any additional training, and report improvements in inference speed with minimal accuracy loss across various tasks. Our experiments demonstrate that by adjusting pruning parameters, LazyLLM achieves significant TTFT speedup while maintaining better accuracy compared to baseline methods, highlighting its efficiency in processing long content. Section: Impact on overall generation speed. In this section, we evaluate how our proposed method influences the overall generation speed. We analyze the percentage of prompt tokens that are computed and the speedup in generation, as shown in the table labeled average token. We observe that the percentage of tokens computed by LazyLLM is less than 100%, which means that not all tokens in the prompt are utilized by LazyLLM by the end of the generation process, even though the model theoretically has the capacity to use all of them. The computations in the feed-forward neural network layers increase in a linear manner, while those in the attention layers grow at a quadratic rate with respect to the percentage of tokens computed. A lower percentage of tokens computed indicates that LazyLLM reduces the total computation, thereby providing additional speedup in the overall generation process across various tasks. Next, we analyze the impact of where we prune tokens within the layers and how many tokens we prune. We conduct a series of experiments using a simplified version of LazyLLM that prunes tokens only once within the transformer. For each trial, we place the pruning layer at different levels of the transformer stack and apply various pruning ratios. We perform these experiments for both Llama 2 and XGen, and we visualize the results in the figure labeled HP ablation. Our findings reveal that both models exhibit a similar trend. As anticipated, when we prune at the same transformer layer, the model's performance gradually declines as we retain fewer tokens. Additionally, we find that pruning in the later transformer layers consistently results in better performance compared to pruning in the earlier layers, indicating that the later layers are less affected by token pruning. Based on these insights, we suggest a strategy for progressive token pruning in the section on LazyLLM inference, which involves pruning more tokens in the later layers while keeping more in the earlier layers, thus optimizing the balance between efficiency and performance retention. Finally, we characterize the internal workings of the model concerning the token pruning logic. We aim to understand the fractions of prompt tokens that are cumulatively used and, conversely, those that are not used. This cumulative token usage can be understood as the size of the key value cache at each step. The figure labeled layer analysis presents these cumulative prompt token usage figures for each stage of LazyLLM. Our analysis supports the idea that many tokens are never selected by the model, even though it could theoretically use all tokens in the prompt. Since our model maintains accuracy on the tasks, we conclude that it effectively discards tokens that do not impact the quality of the output.